afternoon, everyone. My name is Tim Fortier. I'm the Communications Coordinator with New Hampshire Municipal Association, and thank you so much for joining us for this 2020 webinar series. In particular, this webinar, Intersect, VHB's innovative platform for developing traffic volumes, or as it's been rephrased, innovative data collection using big data analytics. I am delighted to introduce to you two gentlemen from VHB who will be part of this presentation. As Director of Transportation Systems at VHB, Amir Rizavi is experienced in the management of traffic, parking, transit, and pedestrian studies throughout the Northeast. He has worked on a wide range of transportation, real estate, and infrastructure projects, including environmental reviews pursuant to state and federal guidelines. He works regularly with state and local transportation agencies, as well as municipalities, on major environmental impact statements and multimodal transportation corridor studies. Good afternoon, Amir.
Good afternoon, Tim. Welcome, everyone. Thanks for having me.
And thank you for joining us. The second presenter is VHB's Director of Applied Technology, Steve Anderson. He's responsible for directing the activities and expanding the use of geospatial and innovative technologies and applied technology, both internally at VHB and external to VHB's diverse client base. His background includes over 35 years of experience planning, designing, and implementing GIS and related technologies for local, regional, county, state, and federal governments. Thank you, Amir, for advancing the slides so our members can see who you are. And Steve also has extensive experience with multiple GIS platforms, including Esri, Google, and open source. But most important, Steve is on vacation in Florida, and he's taken time out of his busy schedule to be with us today. So I can't thank you enough, both Amir and Steve, for being with us today. Good afternoon, Steve.
Thanks, Tim. Thanks for having me as well.
And just a quick housekeeping chore. As you know, members, we will package this up as a YouTube video and have that with the PowerPoint presentation materials that we'll send to you by Friday. They will also be on our webinar archive. We encourage you strongly to forward these materials to your municipal colleagues and friends who were unable to join us live for this presentation today. But with that said, I would like to also remind you, if you have a question for either of our presenter, put it into the Q&A chat function. At this point in time, we're going to answer those questions at the end of the presentation. So with that, I'd like to turn the program over to Amir.
Thank you, Tim. Well, thanks everyone for taking the time this afternoon. Thank you for your interest in our discussion today. I'll start off by saying that at VHB, we've been talking about using probe data much before COVID-19 hit. And we've spent the last 8 years working with big data. And that has enabled us to build a lot of relationships with data providers. And what's unique with how we do things is that we have an applied technology group that works closely in conjunction with the transportation professionals. And what we've come up here today is with the transportation planning tool that combines big data analytics and traditional traffic analysis to estimate traffic data, traffic volumes under normal pre-COVID conditions. I want to say that this is not just a COVID solution. COVID served as a catalyst for us to move this forward. But this is something that we see as the future of data collection, the future of volume estimation on the roadways. So when COVID hit, I mean, obviously we saw a lot of cars vanishing from the streets, a lot of major corridors saw reductions of about even up to 75% of vehicles. And traffic volume data, as you can imagine, serves a lot of important purposes, whether it's traffic impact studies, long-range transportation planning, signal warrant analysis, real-time operations, forecasting, and so on. So when there was no traffic on the street, it clearly created a big conundrum for transportation professionals in terms of how to collect traffic data when there's no volumes on the street. Now, some jurisdictions, when COVID hit, some jurisdictions immediately came out with directives and said, we'll embrace big data. We want to collect volume information. We'll use big data. Some of these examples are shown here: Virginia DOT, MassDOT, PennDOT came out with these, and some others. Which is great. But they didn't say how that would happen, and that's what we're here to talk about. We're here to talk about, how we're able to use our tool Intersect to identify and estimate traffic volumes at intersections. And we like to call this as Intersect 1.0, really with the focus on development of intersection counts. This has a significant potential to expand into a lot more applications. And again, just to reiterate, this is not just a COVID situation. It's not something that is just applicable during the pandemic, but this is post-pandemic as well. And again, we see this as a future of how traffic counts will occur going forward. Now, traditional data collection methods such as camera counts or even manual counts or ATR tubes were out the window when COVID hit. Probe data essentially includes data obtained from automatic vehicle identification, cellular geolocation, connected vehicle technology, global positioning systems, vehicle transponders, etc. Now, in order for us to move this forward, our first question, our first issue was really there are many data sources out there, but how do we identify the right data source? It's important for us as professionals to ensure that we stand behind our information. The data, obviously, as I said, feeds into a lot more things, and it was very important for us to make sure that we are comfortable with that and we're able to look under the hood. As I said, VHB, since we've been working with big data for the past 8 years, we had a lot of relationships with several data providers. For this particular effort, we decided to go with INRIX as a partner because one of the main reasons being that we were able to see under the hood. But I'm now going to hand it over to Steve to walk you through some of the different data sources and go into the details of how we went through that evaluation process and then how we ended up picking INRIX and what are some of the things that we can do using probe data. Steve?
Yep, thanks, Amir. Yeah, so as Amir said, we've been working with big data for about 8 years now. And what we did about 8 years ago is we created what we call our Data Fusion Center. And our Data Fusion Center is it's a cloud-based big data environment. It literally contains hundreds of different data sources and at this point, hundreds of terabytes of data that actually exist in that system. We use on a regular basis about 20 different commercial data sources on different projects that we do work for with state and local government agencies. And through that experience, what we've learned is that there's not one data set out there that can actually solve every problem that you're trying to solve. And we've learned some of them have different strengths and weaknesses that actually help you solve a problem better depending on the problem you're looking to solve. So for this particular effort, we shortlisted a short list of those potential sources down to a number of top contenders that are shown on this matrix here. And some of the key characteristics that we took into place and what we're looking for is looking at the granularity of the data. So how granular can we actually get? Can we actually measure an individual device or an individual vehicle moving so we could actually track it and do calculations with it? We also look at the penetration rate of that. So are we getting a statistically significant enough sample of data that we could work with so the measurements are accurate that we're getting out of the other end? Coverage is another important characteristic that we look at. For this particular problem we're trying to solve, we want data that goes to all roads so that we're not just looking at data that may cover only state level roads. And then the last area is timeliness of the data. So what we typically needed to do in this case with the pandemic going on is we needed to go look at historic data so we could see what conditions looked like prior to the pandemic, also looking at conditions through the pandemic and now that we're coming out on there. And now we're looking at being able to actually get data on a real-time basis. So when you look at this matrix, there are a number of data sets on here that we have a lot of familiarity with. Here is a really good data set that we've worked with. We actually have a fiber connection between our office where I am today down in Orlando and Florida DOT, and we actually connect into the real-time data that is produced from here. Some of the strengths of that data set lie in the fact that we could get this real-time connection to the data as well as the historic information. So we could do comparisons between the conditions that exist today and conditions that used to exist at past times. With that fiber connection that we have, we receive sensor data about every 5 seconds. We get different incremental data that we store. We do those real-time comparisons with the historic traffic patterns, and it allows us to do things like actually measure congestion or look at bottlenecks that might be happening on a real-time basis. Now, we've done this for both Florida DOT and North Carolina DOT, and we've been able to leverage this to help them with prioritizing their spending, identifying locations that have the most significant congestion, speed issues, or areas with significant bottlenecks that are occurring, and actually understand the cause. Now, for this problem, the challenge with the HERE data is that the data is really, really good on the state and interstate roads, but it doesn't have as good coverage for local roadways. So if we wanted to get into more rural areas, like an area in New Hampshire, it might not be the best source to use for this problem. Verizon data is another data set that we've worked with quite a bit. It's really good for micro simulation. We've used this data to measure at a major football stadium the movement and dwell time of fans commuting in and out of the stadium, so we could get to that granularity of really understanding where people are going and where they're moving to, the amount of time they spend in a particular area when they leave those areas and where they go to from there. But the biggest weakness with the Verizon data is getting the data at that granularity is actually a project when you work with them. It's not something that's available all the time everywhere. So not being able to have that data on a timely basis makes it a challenge when you want to be able to do a traffic count or turning movements anywhere across the country. Replica is another data set that we're very familiar with. It's probably one of the most comprehensive data sets on the market. Replica is a company that is a spinoff of Google's Sidewalk Labs. They have 65 million Android cell phones that they're able to get data from, 3 million iPhones, about 65 to 70 million commercial connected vehicles, and 150 million personal connected vehicles across the country. We've used this data for large scale projects where we want to look at an entire population and understand how that population is moving. It's really excellent for these large OD studies and understanding the total movement of people. But the biggest weakness with this is actually getting the data at a granular enough level to actually understand the movement of a particular vehicle or a small group of vehicles moving through an intersection. They typically provide the data to you at a census tract basis. So those micro movements or the device level or intersection level becomes a challenge. But it's really useful data set for helping things like transit agencies understand what was going on pre-pandemic, how things changed during a pandemic, and now how as people are starting to return back to work, what are those patterns? The next data set that's on there is a data set called WeJo, and WeJo is a data aggregator that provides very, very detailed device level data. They actually provide it to you as point level data sets. We get a ping from each device every 3 to 5 seconds apart. We have to take that point data and conflate it to a street network to do this type of analysis. But because of the small time increments and the granularity of it, it's really good for doing this type of a calculation. And where we found it's particularly useful is doing analysis like queuing at signalized or unsignalized intersections where we need to track them. The one challenge with that is the penetration rate, or that the volume of data we get there isn't quite as high as the last provider that I'll talk about, which is INRIX. So INRIX is the data that we've chosen for this platform. If you want to go to the next slide, thanks. There are a number of products that INRIX actually has. The data that we're using is what they call their TRIPS path data set. It provides granular probe data, cell phone, location-based, and connected vehicle point data. It actually allows us to see the individual device and aggregate that data so we could follow the location of the vehicles as they're moving, perform other calculations we need to actually do the turning movements. Depending on the geography, we could go back approximately about 2 years for comparison and calibration with historic data at this point. And the capture rate is pretty good. The most current data that we're getting now off of that is typically in the range of 15 to 25% capture rate on a particular day. So if you go to the next slide, Amir, what we're actually doing with this data, just to give you a sort of an understanding of how we use this data and how it flows, I'll talk a little bit about the data side and then turn that over to Amir. One of the first common questions folks have for us is, if you're looking at data at this granularity, how do we maintain anonymity in the data itself? So what you could see here is a representation of it's a grid pattern that gets created. So we take the raw data, and rather than having that location when a vehicle turns itself on is when you first get a record from the vehicle itself, and we don't want that to land on somebody's garage. So we generalize that starting point location to a grid pattern like this. So we'll pick the vehicle up on one of these grid points. Then if you go to the next slide, Amir, what happens next is what we're really concerned with is when the vehicle actually gets on the roadway system itself. So we'll conflate that data, snap the data to the roadway system, and then we're able to now start tracking the vehicle moving across the roadway network that's out there. And we're able to also pick up other characteristics. Like in this case, we know that this vehicle is traveling on US 192. We know the speed limit on that road is 45 miles per hour, but from the data source itself, we know that it's actually traveling at 30.8 kilometers per hour right now at this point in time. Then as the vehicle carries along its trip, there's a lot of other characteristics we could pick up and other applications we could use the data for. In this case, we could see the vehicles actually crossing a bridge. We could get the speed of that vehicle, and then we could look over a longer time frame to understand, well, how many vehicles are traveling, across a particular bridge at a point in time or during a time window. We can also see when the vehicles has stopped moving. So in this case, the group of vehicles have stopped on a segment that's at an intersection. So we know that the vehicle actually stops at a light and sits for 10 seconds. So we go look at congestion that might be happening and dwell time that's actually taking place as it moves through the network. Now, what the data we're dealing with is a tremendous volume of data. This graphic shows you just the starting trip location of all vehicles in one day in New York City, which, to give you an idea of what one day looks like, it's about 850,000 trips that started in New York City in a typical day. And we're now doing a project. We've been testing all of this data for using it for all of the turning movements and ADT calculations and PADT calculations for North Carolina. So we have data for an entire year for North Carolina, and it's about 62 terabytes worth of data that we're working with, and literally billions and billions of records of information. So it's a large volume of data to process, but what Amir will now describe is what we do with that data to actually solve this problem.
Great, thank you, Steve. So we'll now get into the actual technical details of Intersect itself, and I'll walk you through the process. So it's essentially a 4-step process where the first step, we're leveraging the probe data. Step 2 is identification of control points. Step 3 is ensuring a balanced flow approach. And finally, step 4 is validation. And again, I'll walk you through each of these steps in great detail. So step 1 is really identifying, taking that probe data and identifying where vehicles are going. So if you take point A, for example, what you have is a bunch of dots, and we really need to track them and figure out whether some of them are going left, some of them are going through, some of them are going right. We need to figure out who's doing what. So that's really our first step. We're identifying the turn percent volumes. Now, one thing that, just to add in here, probe data is available all the time. So it's almost like a continuous collection process. We are able to obtain data for any time of the day, any day of the week. We're able to determine seasonal adjustments because you're able to get that data for multiple days, multiple months. So once we get through the step 1, this slide is really showing you just a formula behind it. And as you can see, it's just showing you what's turning left divided by the total volumes at that location. Step two is identification of control points. So now what are control points? So these are permanent or portable count stations or sensors that enable us to provide historic volumes on those streets, on those roadways, on those approaches. Now, this might also be historic count that might be available. Now, if we have that at that location on the approach, that's great. If we don't have it, we'll use information that's in the vicinity of the intersection that we are looking at. And if we don't have that, then we will go with capture rates. Now, capture rates is essentially, so just as you can imagine that not every vehicle that's out on the street gets a ping. So there's only a certain percent of vehicles that are traveling through the intersection that are actually captured using probe data. So our step here is to try and normalize that information. How do we get that from a smaller percent to a higher percent? If we don't have the control point information, then we are able to get capture rates from INRIX in order to normalize that. When we get the probe data, we typically go out and get data for about 6 weeks or 8 weeks. We do this because we have done multiple tests. We have obtained information for a single day. We've done the tests for 3 days, and we've done the tests for 6 weeks and beyond. And we've seen that the accuracy there's a significant change in accuracy. From 1 day to 3 days, it comes down from about it's 20% less accurate for a single day. 3 days, it's within a 5% accuracy, and then once you go 6 weeks and beyond, it comes down to within a 2-3% accuracy. So when we do this effort, we obtain probe data for at least 6 weeks, and this really makes it, when you put this in perspective, in comparison to the manual counts, you have a much larger sample size. When you do manual counts, you're going out on a typical day for the specific peak hours, but when you're using probe data, you're actually able to get that now for you have a much larger sample size. You're able to do that for 6 weeks or 8 weeks. So we feel that's a lot more accurate than the manual count. So that's just to give you a sense of how the control points play a role in this effort. This is again the nomenclature. As you'll see a bunch of formulas as we go down. The TA1, TA2 are essentially the control point volumes that we're using in our algorithm. So just to give you a sense of what those mean. Now, on approaches, there might be sinks and sources, which could be driveways or other streets or retail establishment. So this this platform also takes into account any sinks and sources that might be where vehicles might be lost or vehicles might be gained. So again, this slide simply goes to show that we're taking that into account. Step 3 is a balanced flow approach, and in very simple terms, this is to make sure that whatever volume is going into the intersection along the different approaches matches what's coming out. Now, that might seem obvious, but when we're talking about a bunch of data points, and as I said to you in step 1, where we have to track it and almost do many ODs, many origin destinations, we have to make sure that that is following through. So for example, just to make sure that the total westbound volume coming off of Route 25 would be 3 plus whatever is coming through here, plus whatever is turning left here, right? So we just have to make sure and run those checks to ensure that those volumes are being balanced. And again, this is also goes to show the nomenclature. The VALT, VATH, VART are simply the specific movements now, and that's how they're going to be notated. And then this is formula for standard deviation. So when we have the control points, as I mentioned earlier, the TA1, TA2 divided by the total volumes when you break down per movement and you look at the probe data information and you do that comparison, you want to make sure that that deviation is as close to 1 as possible. So again, these are steps that run in the background. We're just providing you the details to give you a sense of the robustness behind the methodology. Um,
Amir, this is Tim Fortier. We have one question that came in. I think it pertains to the previous slide. Are vehicle types classified?
So we are able to classify it as personal vehicles or commercial vehicles. So we are able to determine, if it's a heavy vehicle, we are able to determine that. We're not able to classify it based on the number of axles or something like that, but we are able to determine it classified between a personal vehicle and a commercial vehicle. Hope that answers the question.
Thank you.
Sure. So then this slide is really just to show how many permutations take place in the background or can take place while making sure that standard deviation value is as close to 1 as possible. If it's a three-way intersection, it's over 1 million potential combinations. And if it's four-way, then it's almost 3 billion permutations. So it is pretty significant when you look at it from that standpoint. And then the step 4 is the validation process. So this is just to make sure, once we have this information, it's making sure that this is real, this actually works. So we're actually going to show you, I'm going to show you a couple of examples here in terms of how we went through the validation process. This is an actual project. And then once we're done with it, we'll also walk you through a couple of case studies. So just to take you to this particular project, this was an effort we did out on Long Island in West Islip. And this was a beach going area. So, and this was for a hospital. So the client wanted to get an understanding of, because the summer volumes made a difference there because of the type of area, they wanted to get volumes in summer and in fall. So in 2019, they were able to go out and get fall data. They missed the summer period, and they were planning to do it in summer of 2020, but COVID hit, and they couldn't do that. They went and counted anyways, but clearly they weren't comfortable with the counts. So when we used our probe data, what we ended up doing was, so they wanted us to come up with summer 2019 volumes, and what we ended up doing was, because we are able to go back in time, we were able to look at the summer 2019 volumes during the same period that they counted in summer 2020. We also had the summer 2020 volumes. We did a comparison of the probe volumes for summer 2020 with the actual volumes that was obtained. We were able to obtain certain factors and then apply that and come up with the summer 2019 volume. So we were able to go back in time based on historic volume information and come up with the data. And then the validation that took place, really, this slide is simply to show you some of the end products. So we are able to provide full turning movements. This is for different time periods that we provided to them. But what was interesting was they were also able to see the trends. And what they ended up seeing was that during summer, the volumes actually were a little higher, whereas during the weekdays, the volumes were a little lower. And this made sense from a local perspective, and we talked to the locals there, that during the work days, people were really not commuting to work, they were working from home, but during the weekends, they were actually going out. They were trying to get out a little bit and go to the beach. So this was just one example, just to show you that process that we went through. The second example was really from New York City DOT. So when we presented our approach to them, they actually said, well, we're going to do a blind test. Why don't you, they gave us a few intersections. This is just an example. This is just one intersection. They said, well, come up with volumes at 4th Avenue and Union Street in Brooklyn. We want to see how that plays out. And we went back and we showed it to them. And when we first showed it to them, it was interesting. There were some differences, and we asked them. So our data from the probe data was from December 2019, and we asked them, well, when was your data? When did you go out and do manual counts? And they said it was from October. So we actually went back and we did a comparison of October 2019 and October from the probe data and the manual counts, and you can see that the correlation significantly improved and is significantly closer. So this for this particular intersection, the north and the southbound volumes cover about 85% of the intersection volume. So you can see the southbound, for example, is 93% here and 94% here. So a couple of things we do when we do the comparisons are we do the individual turn percents and then we do the percent for the entire approach. So you can see the 93, 94, very close correlation. Similarly in northbound, 90 and 91. Now in the east and west, you might say, oh, this is 47 and this is 63, but the overall is just showing 1%. The eastbound, westbound volumes were significantly lower. So for example, you could have 20 vehicles traveling east going through in the manual counts, and the probe data might show 23 vehicles, and that can be a 15% difference. So just to give you a magnitude, that's why that overall approach percent is still very low. So that gave a significantly close correlation. So just to kind of sum this up before we go through some of the case studies, there's a significant benefit to using probe data. First of all, we have 24/7 accessibility here for any intersection. We have year-round availability, so we don't have to. We can account for summer, non-summer, holiday period, non-holiday period, and best of all, we are able to do this from the convenience of our desks. You don't have to send a crew out. You don't have to worry about safety situations. You don't need permits. You don't need to close down roadways and things like that. So overall, there's a lot of physical aspects here. But more than anything else, this is also, as I said in one of the earlier slides, because we're getting a larger sample size, because we are going over 6 weeks, 8 weeks, that data is robust, and it's not just based on a sample or a snapshot in time and it's 1 day. This is actually, you're getting that information for 6 weeks or 8 weeks. So we feel that this offers a higher reliability. So I think with that being said, I'm going to move on to case studies, and we have 3 case studies that we'll walk you through, and we wanted to give you a flair for where this can be used. So the 2 examples I showed you, one was a suburban area out, like I said, in the suburbs on Long Island. The other was in Brooklyn. It's a very urban setting. So if you're able to use this information, whether it's a rural setting, an urban setting, a suburban setting. So the first one was for University of Southern Maine. This is a very small study. Again, this goes to show whether it's a smaller study or a larger study as well. This is more on the rural type area that we were looking at, and we were just looking at 2 locations here. It had low volume of traffic, but the university was transitioning, and they wanted to accommodate a new 600 to 580 bed residence hall. And so they wanted us to look at a couple of intersections and see how traffic patterns might change. And we were able to do that for them. And we actually moved the project forward because otherwise this project would have stalled. So we were able to submit it to Maine DOT. The second project is down in Virginia. This was an effort for Loudoun County, Virginia. So Loudoun County is our client, and they also needed Virginia DOT to sign off on the process and the methodology for this. So this is a medium type project. This was an 11-mile stretch of a corridor, and you can see a bunch of intersections there. There are about 16 intersections, so 13 intersections that are on that corridor. And what they wanted us to do was they were shutting down a portion of the road, and they wanted to see how traffic patterns had changed. So we were able to provide them information for these different locations. And they had volumes at certain locations. They had a lot of gaps. We were able to fill those gaps and also correlate it to those volumes. So this was another example where we were able to move the project forward. Otherwise, the project would have been stalled. And it was interesting. This was a great example where we were able to show that the level of accuracy in capturing the travel behavior was really better than what we saw when we did traditional manual counts. I'm going to hand it over to Steve to talk through our larger just one other note on this. This is just the output. So on the left-hand side, you can see how we're able to provide the volume information for the different intersections. But one other thing that we did for that project in Loudoun County was also determine speeds and travel time. So we were able to break it down. So this was for Western calibration. They wanted us to provide them with backup information, and in order to calibrate it, they needed speeds and travel times along the corridor. So we were able to give them breakdowns. You can see the speeds are broken down by 15 minutes for the different approaches. Similarly, for the travel time, we ended up doing about 12 different travel runs for along the corridor. So again, going back to Steve's point about the different aspects that can be provided using this information, we were actually able to do this on a real project as well. And I'm now going to hand it over to Steve to talk about our effort, large-scale effort for North Carolina DOT.
Yeah, thanks, Amir. So this is a project that I started to mention a little bit earlier. So VHB has been working with North Carolina DOT to manage their statewide traffic program for about the last 4 years now. And what we had done is we had built a system that tracked all the requests for all the projects that were going on across the state, to basically remove any duplication of effort that was going on for the state and better kind of manage that whole workflow process. But when the pandemic hit, that whole program came to a halt for the same reasons Amir had mentioned before, that there just wasn't the volume on there that they could continue doing it. So we started talking to them about testing this Intersect approach as a replacement way to go back and actually complete the effort out. And what we've done is we've just completed doing 92 sample locations across the state. They cover everywhere from the coastal area where the Outer Banks are, where there's very heavy traffic volumes during vacation season, to mountainous areas where traffic volumes change drastically in more of the fall areas, to the typical seasons across the year. And we've collected, we have data for 365 days for the entire year across the entire state that we could actually do these measurements and these calculations. So from doing the tests, we were able to cover about 100 different counties across the state. We're now actually expanding this out to 1,000 locations that they want to do this to sort of complete the analysis, because the tests went very well with the sample locations that we've done. But the ultimate goal for them is to be able to do 55,000 locations on an annual basis. And you can imagine if you tried to do that using manual counts, it would be an effort that would almost be, impossible to do because of the cost associated with this. But from here, we're able to actually do this and actually see how probe data can actually compare to actual data. If you go to the next slide, Amir, this will just show you a graphic that we have where you can actually see the differential with the measurements that we're actually able to do now, comparing the probe data to this. We're running all the statistical analysis on this, and as I said, the results are coming out very, very strong, very positive, to where they're actually looking at replacing their entire program to going with a probe-based approach rather than doing it with traditional count data. So I think at this point, I think that is the end of our presentation. I saw at least one question that had come in.
Yeah, I don't know if you can read it or see it, but we do have a statement with 2 quick follow-up questions. It looks like the platform being used is ArcGIS. Is it web-based application or desktop? And any thoughts why this particular platform was being used?
Sure, I can answer that. So the platform itself that we're using is a web-based platform. The screenshots you saw where we were using desktop ArcGIS just to show some of the results in those. But the back end of the system itself is actually built on top of MongoDB and Elasticsearch are the actual big data environment that we're using that are there. We're using OpenStreetMap as the street network to do the analysis, and then we're kind of using the Esri ArcGIS as a presentation layer, I'll call it, so we could actually show the results on top of a map.
Very good. This is getting pretty specific, but on the previous slide, what are the R square values for the last slide? So it'd be the slide before that. Yeah.
Amir, do you know what the final numbers were on that? I think that may be a good question for us to follow up with, that we're
Right.
actually finishing all the statistical analysis, and we could actually give you that breakdown of what they are, because they did vary by location and different areas and time of year as well, since we were running it across the whole year. But would be happy to follow up with this with providing the exact
Okay.
numbers, so we're not providing the wrong numbers.
Yeah, thank you, Steve. I think we'll do just that. So if the webinar participant can hear us, that will be the game plan, is that we'll follow up with you back channel. And I guess this is, interesting presentation. They appreciate it very much. So I'd like to take this time to thank Amir and Steve for their presentation today. Also wanted to highlight to our members that Amir is the feature article in our May-June issue of Town and City magazine. So if you are interested in this subject matter and want to read more about it, go to our May-June 2021 issue of Town and City magazine, and that's our feature article. The last thing I wanted to do is just remind our members that these materials will be packaged as a YouTube recording, video recording. We'll be sending that back to you with the PowerPoint presentation materials by Friday. You can always access these webinars in our webinar archive. So I'd like to thank our members who attended this session, and thanks again to Amir and Steve. Great presentation. And Steve, get back to your vacation.
I'll try. Thank you. Thank you for having
Tim.
us.
Thank you.